Okay, welcome to the final lecture of 304. So what we're going to do today is we're going to discuss P and NP one last time. So recall that P is the set of all languages decided by deterministic polynomial time Turing machines, and NP is non-deterministic, but it's still polytime. And the motivation was we want to have algorithms that run quickly. And the NP class we can think of as um, all the languages that have polytime verifiers. So the class of NP is the problems that we can check quickly. P is the ones that we can solve quickly. And the fundamental question is whether P is equal to NP or not, and we don't know the answer. But what we saw last time was we had this concept of NP hard and NP complete. So hard just means that if we can solve this NP hard problem fast, then we can solve every problem in NP fast. And we saw that there are some languages that this is some undecidable languages are NP hard. So we introduced this notion of NP complete, which means that it's still hard, but it's within the class NP. So if a problem can be solved efficiently that is NP complete, then we can solve all problems in NP quickly too. And what we saw was that, oops, that was too much, CNF sat, or at least I gave the outline for the proof, is NP complete. And this is by Cook and Levin in the 1970s. It wasn't in one paper, but it was, I'm not even sure if they even worked together, but the result is celebrated as like the Cook-Levin theorem. Okay, so what we wanted to figure out was, well, the proof of this result is actually quite complicated. How do we show that some other problems are NP complete? Well, we saw this notation a less than or equal to b with a little subscript p here. And what this represents is a polynomial time reduction. So this is a reduction that takes poly time. So if we have some instance of the language A, which could be CNF-SAT or anything else, then this says that we can transform the instances of A into instances of B such that the answer of whether the original input is in A is the same as whether the transformed input is in B. So W in A, if and only if we apply the reduction to that input, is in B. So it's really important that the answer is the same on both cases. Yeah, and that's all that we need. So remember the clique problem that we have discussed several times, and I'll just refresh your memory. So this is always going to be a pair GK, where G is a graph and has a K clique. And remember what a clique is. So a clique is a bunch of vertices where every single edge among every possible pair is present here. So that's a K clique. So what you could do is just try all possibilities, but what we saw was that this is in NP, and the reason is we can have a polynomial time verifier for this, where the verifier just takes k vertices, and we'll check every pair among those k vertices, whether or not all edges are present. If any one of them is not present, then the verifier rejects, and if all of them are there, then the verifier accepts, and that takes polynomial time. So what we'll show here is that Clique is NP-complete. And so what do we need to do here? Well, we just showed that it's in NP, so the only thing we need to do is to show, so it suffices to show that the Clique problem is NP hard. Okay, so in NP hard, what that means is that every problem in NP reduces to this one, Clique. Well, we could do the proof like Cook and Levin did, but that's way too complicated. What we're going to show is that that the CNF SAT problem reduces to Clique. Well, why is this enough? Because if every problem reduces to CNF SAT because it's NP-complete, well, this says that we could just take whatever the transformed input is for CNF SAT and apply another reduction to the Clique problem. So this will imply that Clique is NP hard. So how do we actually show this? So how do we show that this reduction right here? So recall that what the CNF SAT problem is, we're given a Boolean formula phi in conjunctive normal form, and it is satisfiable if and only if we apply some type of reduction which transforms this formula into a graph G and an integer K, and G has a K clique. So notice that the answer of whether it's satisfiable is the same of whether G has a K clique or not. So how do we actually transform the formula into a graph? So the idea here is to use something called a gadget. So this is something called a gadget style proof. And what is this going to do? Well, what we're going to do is to have for each of the clauses a vertex gadget. So one thing that we'll have is a vertex gadget. And let's just say that the clause is x1 or x2 or up to xn. And recall for the CNF SAT problem, the length of a clause can be anything. I guess any finite number. But so what is the vertex gadget here? Well, I'm going to use a different color so it's easy to distinguish. So I'm going to make a bunch of vertices where the vertices are going to correspond to the clause that we have here. So for each of the literals appearing in the clause, I'm going to make a single vertex for them. So if we had x1 or x2 or x3, then we're going to make 3 vertices. x1, x2, x3. And if we have another clause, which say happens to have an x1 in it, we're going to have another copy of that variable x1. So in general, we could have many copies of the same vertex appearing in this graph. So now what we need to do is to connect these vertices up in some way. So let's see. So what are we going to do here? It's something that I'm going to call an edge gadget. And so here's the idea. So let's just say that we have, let's call this clause 1. This one is clause 2. We have a bunch of vertices. Clause 3. And then finally clause M over here. So what are we going to do? Well, what are we going to do is no vertices are going to be connected to another one within the same clause. So the only edges can only go between from one clause gadget, one vertex gadget, to another vertex gadget. But we're not going to put every edge in. So let's say that if we have xi over here and not xi over here, then we're not going to form an edge between these two. So we're not going to make an edge that connects those two. So we're going to form all edges except the following ones. So except within the same clause, or in different clauses, and the literals are complements of each other. And I'll do an example of this. Complements of each other. So let's do an example of this. So let's say we have x1 or x2 and x1 bar or x3. I should do that better. x3 and x2 bar or x3 bar. So we're going to have 6 vertices. So this is going to be x1, x2. This is clause 1. Then we're going to have 2 vertices for clause 2, which is x1 bar, x3, and then x2, and then we're going to have a third clause, which is c3. So this is c1, c2, c3. And these vertices are x2 bar, x3 bar. So now we're going to connect up all vertices such that we don't hit the ones in the same clause, and if they're in different clauses, they must be complements. So let's focus on this x2 right here. Well, it can marry up with the x1 bar. They're in different clauses, and they're not complements of each other. It can marry up with the x3. It can't marry up with the x2 down here because although they're in different clauses, they are complements of each other. So we're not going to connect those up. Then we're going to, we can connect those two up. We're not going to connect x2 with x1 because they're the same clause. Let's do x1 bar over on the right side. Then we can connect here, connect here. We can't connect to the x1 across. We've already connected to the x2. x3 on the right, we can connect to here. We can't connect to x3 bar. We can't connect to the x1. We've already connected to the x2. We can't connect to the x1 bar. X2 bar downstairs, we've done the 2 vertices on the right. We can't connect to the x2 on the left, but we can connect to this x1. X3 bar, yeah, we've already connected everything we can, I think. Oh, except this one. X1, have we connected everything that we can? Yeah, we have. And X2, I think we did everything we can. So this is the graph that we make. So let's see. So then I claim here that the graph has a k-clique if and only if the original formula was satisfiable. And and we have to make sure that we have k clauses in the first place. So whatever the number of clauses is, let's just say 3 here, then I claim that there is a 3 clique in this one if and only if the formula is satisfiable. I'll just say sat for short. So let's see. So how can we satisfy this formula? Well, one of these two must be false. So let's just say that x3 is false. Then over here, x1 would have to be false, and then x2 would have to be true. So what do we do here? Yeah. So what do we do? Let's just make sure I have this right. Yeah. So let's actually look at this. So we have this variable being the so-called witness that the clause is actually true. I don't care about x1 in this clause. As long as this variable's true, then we're all good. Then x1 bar right here is also the witness for the second clause. x3 doesn't matter here because x1 bar is true. Yeah, so this false right here refers to x1, not x1 bar. That was my I should have made that clearer. So false means that the original variable, not the complemented one, is false, but complemented the variable's true. So that's the witness for this clause to be true, and that's the x3 bar is also the witness for this clause to be true. So then now let's look at the corresponding vertices in the graph, which are this one, and this one. Well, notice what we have. We have a 3 clique because every pair of vertices is there. So let's actually think about this. So why does this work? So whenever you have an if and only if proof right here, we need to prove both directions. So let's do the forward direction first. So let's say that the graph has a k-clique. Yep, it must have a k-clique. Well then, and let's just say that the vertices for this k-clique are v1 up to vk. Those are the vertices in the clique. Well, that means that v1 through vk are in different vertex gadgets. And why is that? Well, notice that we never made an edge between two vertices within the same vertex gadget. So all of these vertices must be in different gadgets. But, well, what does that mean? Well, so now let's look at the original formula that we derived this from. Well, that means that, well, since every edge is present among these, then this implies that none of the VI are a complement of a different VJ. Because we didn't form an edge among the ones, say like from this x2 right here to this x2 bar, we didn't make an edge going from one to the other. And that's why it's important right here. Because if that were true, then these are the so-called witnesses for the clauses to be true. Well, if one of them is a complement of each other, well, in one clause it's true, and in the other clause it must be false because they are complements of each other. So that means, well, what do we do? Well, what we need to do is just pick VI to be true if VI is normal in the graph, and vi to be false if vi is complemented in the graph. And so therefore, since none of them are complements of each other, well, since they're not complements of each other, and they must be in different clauses. So we created this vertex gadget, one for each clause. Well, if all k of these vertices are in different vertex gadgets, well, then they're in different clauses. So that means that by this assignment, this must satisfy the formula, because if it is normal, a normal vertex, and we choose it to be true, well, that means because clauses are ors of variables, then the or in that clause results in the value true. And if we picked false, where vi is the complemented version, well, then vi bar is true, which means that the clause is satisfied. So this yields a satisfying assignment. And we actually don't really care about all the other vertices if there happen to be other ones. All that we care about is that there is a satisfying assignment. So like for the other variables, we can set them to be anything because it just doesn't matter. Okay, and what about the other direction? Well, if the formula was satisfiable, then we can actually use the same idea in reverse. Well, if it's satisfiable, then what we need to do is to pick any true variable in the clause. If it was false and complemented, we can pick that. Whatever you pick any variable that you want in the clause. Well, if you pick, say, like this x2 right here and this x1 bar, I know for sure they can't be complements of each other, because if they were, it would be true in one and false in the other one. Even after the complement, it would be false. So that would imply that in the graph, they would correspond not only to different vertex gadgets, well, and therefore all of the edges would also be present too, because they're in different clauses and they're not complements of each other. So then we would have a k-clique in that case. So the reverse direction is almost identical as the forward direction, just in reverse. So now the thing that we need to check is, does this run in polynomial time? So because if it doesn't run in polynomial time, then we just wasted our time. So does this run in poly time? The reduction, I mean. So by this I mean the reduction. So I claim it does. Well, what is the number of vertices that we have? Well, that is the number of literals in the formula, which is clearly a polynomial in the size of the formula. You can actually say that it's linear in the formula, but a polynomial is all that we really need here. Well, what is the number of edges that we could place? Well, no matter what happens, let's just say that there are n vertices. Well, the number of edges is always at most n choose 2, which is at most n squared. And it could be way less than this, but it's certainly at most this. So this is also a polynomial too. And so therefore, the size of the graph that we have made is polynomial in the size of the original formula. Okay, so therefore, this is a polynomial time reduction. So this is a poly time reduction. Pretty cool. And therefore, CNF sat reduces polynomially to clique. And this implies that clique is NP hard, and so therefore clique is NP complete. Cool. So let's see. So should we do another one? So you can. Okay. So so let's do a somewhat simpler one. So when we have CNF sat, so in the case of CNF sat, we could have an arbitrarily long clause, right? So we can have as many literals in a clause as we want. But in most applications, you very often want to have a small number of literals in a clause. So the problem for which is called 3-sat is the same as CNF sat, but all clauses contain exactly, or I should actually amend this, at most. Yeah, at most 3 literals. It can't contain more, but it can contain less. So we can easily see that 3-sat is in NP, and what is the certificate is the satisfying assignment. And what would the verifier do? Check if the assignment really is satisfying. Okay, so it's pretty clear that it's an NP. It's the same reason that CNF sat is an NP. But I claim that 3-sat is NP complete. And when you start building up a library of NP complete problems, it's actually quite difficult to figure out, okay, what is the easiest problem to reduce from? CNF sat, or we could have done clique, or what? What is the best one to show 3-sats NP complete? Well, this one you can probably guess is CNF sat. And that's generally the one to go for, or 3-sat or something like that. But I claim that we do this. So here we have a formula phi. It is satisfiable for the CNF sat problem if and only if a modified formula called, let's say, phi prime is also satisfiable, having at most 3 literals per clause. And what do? Well, if some clause in the original formula has 3 or fewer literals, then we don't really care. But let's suppose that we have some number of literals, which is bigger than 3. So like x1 or x2 or x3 or x4 or up to xn. Well, what I'm going to do is we're going to make the formula, make this a little smaller. We're going to break down this clause, and we're going to, yeah. So what we're going to do is we're going to make the clause actually smaller. So what are we going to do here? Well, let's just suppose that we have exactly 4 literals in a clause, and then we can show that this is true if you have longer ones. So let's say we have 4. Well, let's see. Well, then what we can do is this. So what I'm going to transform this clause into is two clauses. And what are the two clauses going to have? It's going to be x1 or x2 or a, where a is a new variable, a dummy variable if you like, and then and then the same variable over here, but the complemented version of it, or x3 or x4. Okay, so let's see. So let's say that this clause was satisfied before, which means that one of these is true. One of these variables is true. But let's just say without loss of generality, x1 is true, because it's symmetric for the other ones. Well, if x1 is true, then this clause is satisfied, but we don't know necessarily whether this clause over here is satisfied. So, but then we have this dummy variable which can save us right here. So if I set a to be false, then that means that this clause is satisfied now, which is good. And if same thing is true if x2 is true. If x3 is true, well then that means that this clause is satisfied and not necessarily this one. But then this a comes to the rescue again, and if we set it to be true, then this clause is true too. But now suppose the case where where all four of these variables are false. Every one of these literals is false. Well, this is false right here, false, false over here, false over here. So the only things that could potentially be true and make the formula true is the a variable. Well, if I make a true to satisfy this clause over here, the a variable that is complemented is false, which means this clause is not satisfied. So therefore, we have true for this clause and false for this clause. And so therefore, it's not satisfiable. If instead we made a bar false to satisfy this clause, then this one would be false, and then this clause would not be satisfied. So if this was satisfied before, then we can have a way to satisfy these two clauses. If there was no way to satisfy this clause, then in the context of the formula, I mean, then there's no way to satisfy these two. So the answer really is the same. And then what do you do if we have more? So let's just say we have x1 or x2 or a lot of literals in the clause. Well, then what we do, actually I'm going to make it a little longer so we can see some of the variables. So like n minus 2 or xn minus 1 or xn. So then let's see. So what do we do? Well, I'm going to do this in blue. So what we're going to transform this is into two clauses of the form x1 or x2 or up to xn minus 2, stopping with the x's here, or a, and then and a bar, same thing as before, or xn minus 1 or xn. And so therefore this clause has three literals in it, which is great. And then now all we need to do is to apply the same thing inductively on this part over here to break down this clause into smaller clauses. Well, let's see. So what is the size? So this clearly is satisfiable if and only if the original formula was satisfiable. But so does this take polynomial time? Which is always the question we need to ask when trying to prove this. And I claim yes it is. Well, let's see. So for every two variables right here, for every two variables, we're going to introduce one more variable at most. So for two variables, we introduce one more. So the number of variables, let's just say we had n before, well, at most, we have n plus n over 2, which it's not really important what it is as long as it's polynomial. Well, what about the number of clauses here? Well, let's see. So the the clauses that we only care about are the ones that are longer, the ones that are at least 4 literals inside them. So the at each point, well, we're taking 2 variables away from this clause that we originally had. So for each clause, we can only get 2 times the number of literals in that clause, because we get two. Is that right? Um, so we get a clause. Well, actually, it's less than that. So we get a new clause for every 2 variables in each clause. So at worst, what can happen is the number of clauses will be multiplied by 2 at most. It's certainly less than that, but the number of clauses is certainly at most twice the original number of clauses, which is also polynomial. And therefore, this effectively shows that, oops, I did the wrong direction. So CNF sat, poly reduces to 3 sat, which implies that 3 sat is NP complete. Cool. So what I would like you all to do now, before Wednesday or before Friday, is to send me questions on Slack or by email, and I can do a review video for the final if that's something that you would want me to do. So it's been great giving you lectures, and hopefully I'll get some questions and I can answer them then. So I'll see you then.